Welcome back, scholars. I am going to record part two of chapter 12. What we're going to do this time, I introduced analysis of variance and talked about the logic behind it. So now we're going to work on and work through the computation for analysis of variance. We'll talk about hypothesis testing, how you state your hypotheses, how you will then compute your statistic and then make that decision, and then also setting your critical region. Right. So we'll use. I'll show you how to use our new table, new F table, to determine what our critical region is for that F value, and then to be able to make that decision after we find our F ratio. Okay. But again, we remember those two components of variance. Again, we talked about between group and within group. And so we're going to talk about now how are we going to calculate those things with computations and the data that we have. Okay. So I'm going to share my screen and then we'll walk through. Let's see real quick. Let's go ahead and share my screen here. All right. So I'm going to be moving back and forward through sharing my screen, sharing the slides, and then also I'll come out of sharing my slides to go very, very large screen for what you see on the screen here, on the whiteboard there. And so I'm going to be switching back and forth. Hopefully, again, if you need to pause the video, please do so. But here are the notations that we'll be using. And some of these are new. These are not universally accepted. So everyone has their own way of notating a lot of these different things. But if we look at the number of treatment conditions, that's little k. So little k, again, for the example that we'll be using is 3. Okay. So you'll see on the next slide how we utilize those variables. Okay. The number of scores in each treatment, N1, N2, N3, N to infinity, that is the number of scores in each sample, right? So if I have 3 treatment conditions and each treatment condition has 10 scores in those treatment conditions, then N1 would be 10, N2 would be 10, and then N3 would also be 10, okay? It says the total number of scores. In order to get the total number of scores, all I'm going to do is add all of the scores in each of my samples, right? So if I have, again, 10 scores in each of my 3 conditions, then, 3 times N, 3 times 10 gives me 30. So big N would be 30, the total number of scores, okay? Number 4, it says the sum of scores, right? So all I'm doing is I'm doing the sum of scores for each treatment. So for each treatment condition, I'm going to sum all of those scores together, and it gives me a T. So T1 would be a certain number, T2 would be the total of those scores, and then T3 would be the total of the group of 3 for that third group, okay? In order to get my grand total for all of my scores, all I would do is just sum all of those totals that I got in step 4, and that would be my grand total. And we're going to use all of these for computations that we'll see for the formulas that we'll be using, okay? All right, so as you look at the screen, again, here's an example, and we'll be using this example moving forward. So you have 3 different treatment conditions. So you see little k on the screen here. I'm going to highlight it here. Let me point that out. With this laser pointer. So you see k equals 3. Again, I have 3 separate treatment conditions. So k equals 3. Okay. You also see N1, N2, and N3, right? I have six particular participants in each of these treatment conditions, right? So I have, again, 3 6s, okay? Then, if I'm doing big N, I want to know the total number of scores in the entirety of this research study. N equals 18, or 3, right, times 6 gives me 18, okay? One of the other things we talked about was the total of scores for each treatment condition. So T1, if I summed 2 plus 3 plus 8 plus 6 plus 5 plus 6, I'll get 30. the same thing for my second treatment group and the third treatment group is 60, right? So I'm just adding all of those scores together. To get my grand mean or my grand total, all the scores, I'm adding all these scores together, it is 144. Okay, so that is listed here. Okay. You also need to get your mean, because I want to know what those mean differences are. And then one of the other things that you'll need is you're going to square each value, okay, for each treatment condition. So, you square 2 squared, 3 squared, 8 squared, 6 squared, 5 squared, 6 squared. Once you get those squared values, then you'll sum those. You do the same thing for treatment 2, and then the last for treatment 3. And again, those, you got 174, 520, and then 630. To get the sum of all of those squared scores, you just add 174 to 520 and 630, and you get 1,324, and we'll be using that value in our computation. One of the last things that we'll get for our is our sum of squares. You have to get your sum of squares in order to calculate your variance. And so what we're going to be doing is figuring out what that sum of squares is. Once we get our sum of squares, then we can calculate our variance for all of our between group and our within group. And I'll show you how that's done. Okay. All right. So again, as we talk about the structure, one of the first things that we have to calculate is this bottom row down here, right? We have to calculate our sum of squares total, which is then broken up into our sum of squares between groups and our sum of squares within group. Then we also need our degrees of freedom, degrees of freedom for total, degrees of freedom for the between, and degrees of freedom for the within. And I'll show you how to calculate each of those, okay? Once we've gotten our degrees of freedom, then the next thing we have to calculate is our variance. We'll get the variance between treatments is sum of squares between and degrees of freedom for the between. And then we have variance for the within group, sum of squares within divided by degrees of freedom within. Once I get my variance, then I can calculate my F ratio, and that F ratio is going to tell me whether I can make a decision to either fail to reject the null hypothesis or to reject the null hypothesis, okay? And we'll talk about that when we talk about hypothesis testing. All right. So as we go through these examples, right, I'm going to show you how we work through it, right? So to find our sum of squares total, you're going to get your x squared. Again, the sum of those x squareds, you're going to get your g squared, and then that's going to be over n. I'm going to go ahead and show you how to do that here, and then I'll work through all the computations that we need, okay? All right, I'm going to write down a few things. Let me stop sharing this screen, and then I'll show you how we do it. It's going to work from the book, okay? So as we saw from our example, go back, pause the video, go back. We had 3 treatment conditions. Okay? We had 3 treatment conditions, and those treatment conditions have a mean, they have sum of squares, they have various values that we have using those computations. Okay? So the first thing we have to calculate, again, is our sum of squares total. Total. That's going to be sum of x squared minus g squared over big N. Okay? And if we can recall, for our x squared, sum of our x squared equals 1, 3, 4. Okay. Our big N, 17, and our G, 144. So all I'm doing is going to plug values in. Okay. So here, I'm going to plug in value. It's going to be 1, 3, 4 minus 144 squared over 18. Then what I'll do, I just do the calculation, right? So it's 1, 3, 2, 4 minus 1152. And that's going to give me sum total, sum squares total, with SST equals 172. Okay. So that is how you calculate the sum squares total. Okay. You pause it there. Make sure you're capturing this. Make sure you're knowing how we're calculating those things, right? So you 144 squared divided by 18. That's how you got to do it. Let's move forward. One of the other things that we have to calculate, if we're looking at we got to break up our sum squares total into two things: our between group sum squares and our within group sum squares. Okay. So in order to calculate my within group sum squares, remember that I had three sum of squares values. Okay. I had SS1, SS2, and SS3. Okay. And these three values were 24, 34, and 30. So to calculate my sum of squares within, okay, since all of these are within group sum of squares, okay, in order to calculate my sum of squares within, all I have to do then that's going to be it's an equal sum of all of my sum of squares. Okay? All of my sum of squares, 1 plus 2 plus sum of squares. Okay, and that is going to be sum of squares within. That is going to be that is going to be again my sum of squares total. 272. Sum of squares and it's 88. So without having to do any other calculation aside from this next one, okay, what would be my sum square between? Again, all I have to do is subtract 88 from 172, and it gives me 84. So now I have all of my sum of squares. Okay? That's three things that I needed. Okay, I have all of my sum of squares. Okay, so now if I wanted to calculate the sum of squares between, say, I didn't have the sum of squares within. So if you wanted to calculate the sum of squares between, I'm going to go ahead and show you. Okay. So for this one, you're going to need a special formula. So I'm going to put let's do this. So we got sum of squares between. I'm going to show you. Okay. Sum of squares between. Okay. All right. So here is the formula for the sum of squares between. And I'm going to show you what that looks like. Okay. So it's going to be the sum of t squared over n, little n, equals, not equals, minus big G squared over big E. Okay. So we're going to go ahead and solve this out. Okay. We're going to move that equal sign up here. We have, again, if we go back and look at our t's, we have 30 squared over 6 plus 54 squared over 6 plus 60 squared over 6 minus 144 squared over 18. Okay. And then I just have to do my calculation, right? So this first one's going to be 150 Second is going to be 486. Third one will be 600 minus 1152. Okay. Take a step further. Adding all these up, this is 1236. That's 1152 equals 84. Okay. So that gets me to the same value. I just subtracted the within sum of the squares from the total sum of the squares. Again, I get the same thing. This is just a little more tedious, but again, sometimes you may have to calculate, right? And again, you may have to calculate that in the exam, so be mindful of that. Okay, so I have my degrees of freedom, and I have my sums of squares. Now, the next thing I have to calculate are my degrees of freedom. So let's do that. Let's calculate the degrees of freedom. Okay, and let me show you what that looks like before we move forward. Okay, so we just talked about our sum of squares. So now let's talk about degrees of freedom. Okay. So again, those are my sum of squares. We're able to get those things. We're able to calculate those things, which is really, really great. Okay. So that's our analysis of the sum of squares. Again, pause that, write those things down. That's going to be really important as we move forward. Okay. Here is the analysis for the degrees of freedom. Right. So let's go ahead and write this out. We got degrees of freedom total. I'm just going to put degrees of freedom T is big N minus 1. I have degrees of freedom within. Then put W, that is N minus K. And then we have K minus 1. Right. And then here is how I divide the degrees of freedom up. So I have my total. I have to add these two to get the total, right? Those are the two components, okay? That's how we partition the degrees of freedom. So let's go ahead and solve that out. Let me go ahead and stop sharing so we can go ahead and solve this out. All right, so for our example, okay, if you can recall, the big N we have for our example was N equals 18. Okay, the little k we had was 3 because we have 3 treatment conditions. Okay, so we have everything that we need, right? So for the degrees of freedom, for the total degrees of freedom, that's going to give me 18 minus 1, which will give me 17. Okay. For degrees of freedom for within the groups, okay, I have 18 minus 3, which gives me 18 and 15, excuse me. Okay. And then lastly, I have k minus 1 for the degrees of freedom for the between. That's going to give me 3 minus 1, give me 2. Okay. So again, total degrees of freedom, 15 plus 2 is 17. All right. So again, now we have pretty much everything I need, right? We have our degrees of freedom for our total, our within, and our between. We have our sum of squares already written out. And so now we can solve for our mean square or our variance. So we'll talk about that. Okay. So I'm gonna go ahead and share my screen again so we can move forward in the slides. All right. So again, here are the other calculations that I need, right? I have to find the variance for my within group and my between group. I have to find my F ratio, and then we'll be done. Let me go ahead and clear my screen so we can go ahead and solve this out. Okay, so we can go ahead and solve this out. All right, so let's go ahead and move forward so we can get all this figured out, and I'll show you how we do it. And I want to show you, see what's next. All right, and I want to show you what this looks like with a source table. And the source table, which we'll talk about, is how we organize things, keep things really, really organized when we're doing our calculation. Right. So let me go ahead and do this for us real quick, and then we'll move forward, okay? So when we talk about our source table, okay, the source is talking about the source of variance, okay? The source of variance. So we have within group source of variance. Matter of fact, I'm going to do between first. We have between group source of variance. Between. We have within group source of variance. And then we have variance. We also have our simple squares, right? We have our degrees of freedom. We have our mean square. And then we have our F ratio. Okay? So I'm just going to draw a line there. And this is where we go. Okay? So for our sum of squares, if you can remember, okay, if you can remember that, we had a total of 172. Okay. We had a within group. Let's go back. We had a between group, which is 84. Within group is 88. Okay. If you remember our between group, we had 2. Yep, 2. Then we had 15. We had 7. Okay. So that's our degrees of freedom. The next thing that we have to calculate is our mean square. If you go back, look at those formulas. All I'm going to do now is calculate my mean squares from my between, mean square from my within. So we're going to divide 84 by 2, right? So it's going to be 42. And then 88 divided by 15. That's going to give me 5.8. Okay. If we go back to our F ratio, okay, it's going to be mean squared of between over mean squared of within. So what I'm going to do is 42 divided by 5.87. And that should give me 7.1. Right. So that is how I calculate my F ratio. Okay, so I have an F ratio of 7.16. Okay. All right. So let's move along in our slides, but this is the essence of what we'll be doing for the one-way analysis of variance. Right? Let me go back to the slide real quick. Okay. All right. So here's just a check for everyone. It says an analysis of variance produces a sum of squares total of 80. Okay. And it has a sum of squares within of 30. It says for this analysis, what is the sum of squares between? So remember, sum of squares of total is broken down and is partitioned into the within and the between. So you're just adding those two together. So all you would do is 80 minus 30 gives me 50. Okay. Just be mindful of that as we move forward, because you might get something very similar to that on the exam. Okay. All right. So when you're talking about hypothesis testing, right, the null hypothesis, if the null hypothesis is true, right, with that F ratio, the value of F will be around 1, either 1 or close to 1. Okay. Because F ratios are computed with 2 variances, they are always positive numbers, right? So when we talk about our F ratio, and when we talk about how we use our F ratio, the table of F values is organized by 2 degrees of freedom, right? You have a degree of freedom. I'm going to go ahead and put it up here. So we have a degree of freedom for our between and degree of freedom here. 2 is 15. Okay. And so we're going to use those values to determine what our F value is, that critical F value, similar to what we talked about with the critical T, right? We have a critical F that is going to tell us if we can reject the null hypothesis or if we have to fail to reject, okay? So here is what we'll be using, right? So if we're using the a 5% significance level, and we have a F ratio is always going to be one-tailed, right? We're going to show you how that works, okay? So let's go here. Let me share my screen. So let me get out of here, okay? We're going to go here. So this chart here is the F table, okay? I'm going to post this to Blackboard so you'll have an idea of where it is. You're going to need this for your exam, okay? So for us, we want to find our critical F value, okay? And what they've given us is, again, they give us our alpha level, right? Alpha level, we say alpha level is 0.05. Okay? We don't have to worry about a tail. One or two tail test is always going to be a one tail test. And we have 2 degrees of freedom, right? We have 2 and we have 15. The between group degrees of freedom is going to be on the columns at the top row right here, right? So everything up here, that's going to be, again, the between group degrees of freedom, okay? For the within group degree of freedom, that's going to be on the rows here, okay? So if I wanted to find my critical region or my degrees of freedom, for my F value, I'm just going to go ahead and write it up here. Critical. Okay. That's going to be, I'm going to go here. I'm going to go degrees of freedom of 2. I'm going to go down to where it intersects with degrees of freedom of 15, and I should get 3.68. 3.68. So that is my F ratio. That is my F critical. Okay, so I'm comparing what I got, 7.16, 3.68, and given that information, I can reject the null hypothesis. Okay, I can reject the null hypothesis given all of that information. Okay, so let's go back to my slides and we will talk a little more about that. Okay, all right. So again, we got 3.68 and we have a 6.36. These are my critical regions for a 5% significance level. And again, if I went to 1%, I want you to use the chart, go to the 1%. You'll also see that at degrees of freedom of 2 and 15, at 1% is 6.36. So my study shows that there's a significant difference at both a 5% significance level and a 1% significance level, because that 7.16 would fall somewhere outside here, right? Because it's greater than that 7 right there, right? So we know that there is a significant difference between or among those study strategies, okay? All right, so when we're doing a hypothesis test, again, you're using those same 4 steps, right? Use the same 4 steps. Again, you're going to state your hypotheses. You're going to set that critical region, whatever that critical region is, using your degrees of freedom, the degrees of freedom between and within. You're going to compute your statistics. And when you're talking about your computations, these are your computations, right? These are all of your computations. Then the last thing you're going to do is you're going to compare for that step 4. You're going to make that decision. Is the computed F ratio that you got, is it greater than or less than the F ratio for the critical value that you got, right? If it's greater than, then you're going to reject the null hypothesis. If it's not greater than or it's less than, then you're going to fail to reject the null hypothesis, okay? Here are all your different formulas, right? This is what you'll need to calculate your F ratio. All right. Here again is our example, right? We've used this To calculate our F ratio, we've gone through. If you need to go back and look at the computations, but here we've got it all set up on our source table. Okay, and again, our source table is listed here, just like you see there, right on the screen. Right, it's really, really concise method. It presents our results in a really, really clean fashion. Right, you got your between treatments, within treatments, and it calculates everything for you right there for you. Okay. All right. So one thing that we do after we get a significant difference or even any difference, we want to see, we know that there's a difference, right? But again, what is that magnitude of the difference? So just like in R squared, when we did R squared and the t-test, the independent samples and the repeated measures t-test, we're looking at the variance that is explained by the variance or the differences in between those treatments, right? So how much of the variability, right, is accounted for by the differences between those treatments? If it's anything greater than 50%, we know that that is a lot of variance that is contributed to or attributed to the differences between our strategies that we talked about. All right. So if we're looking at our eta squared, I'll show you how to calculate that. All right. So here's our formula for eta squared. Okay. Click off the screen here and I'll show you. Okay. So stop sharing so I can get a full screen. All right. So for my eta squared, all right, if you remember all of our values, eta squared, we have some we also have this is coming for us is showing me how much of the difference, how much of the difference in our between our groups is accounted for with the treatment effect, right? And so now we know all of those values, and we have our simple square root between, it's 84. We know our 84, which is 84. We know our total was 172. Okay? So our eta squared is 0.488 or 48.8%. Okay, 48.8%. That is a large percentage of the variance that is accounted for by our treatment, right? And again, that is a huge effect size. That's a huge effect size. And again, we get to see that as we move forward. Okay. All right. Go back to sharing. Again, moving back and forward. I'll get everything covered here. Okay. That's my beta squared. That's how you calculate it. Effect size is showing you how big the max. If I were to look at this and present this in results section, here is how you would present it. Okay. So again, treatment means you have standard deviations. And again, you can also put other things in tables and graphs, right? But when we're reporting our results for this particular study, right, we knew that we found a significant difference. Okay. So we have F, open parentheses, 2, which is the degrees of freedom for the between. You have your degrees of freedom for you within here. This is the F value that you calculated. P less than 0.05%, because again, we know that that percentage is less than that. Okay, and what that means is we reject the null hypothesis. And then we got an eta squared by effect size 0.488, right? So again, this is how you report it when you do it by hand. In ANOVA, right? If you do it by using a computer, sometimes I use SPSS, other statistical software. Again, you would get everything is about the same except for the p-value is exact, right? So in the last exam, many of you use the actual p-value. I know you use software or some internet tool, right? That's not correct. In order to present it in the form that I want you to present it in, it's going to be presented in this form right here. Okay, So P minus or P less than, excuse me, 0.05. Okay. All right. Here are some assumptions that we have that are related to independent measures, ANOVA. Okay. Independent measures ANOVA, you have three separate uh, uh, assumptions, right? The observations with each sample must be independent. So again, within each sample, each person has an independent observation. They're not related to one another. Each individual is unique, and scores are unique, right? The population from which the samples are selected must be normal. So each individual treatment condition has their own uh, accompanying population, and each of those populations must be approximately normal. And then the last thing, just like in our t-tests, the populations from which the samples are selected must have equal variances. And again, homogeneity of variance happens because we're looking at if the variances are different, then we know that it's going to skew the results of our study, right? So violating the assumption, um, again, it just gives you invalid results. And so you want to make sure that those, uh, when we do that homogeneity of variance test, we want to determine if those variances are similar at all. Okay. One thing that we also do for analysis of variance, right? Again, when we compare those individual mean differences simultaneously in one test, again, we don't again get to see which differences are significant, right? We do know that there are some significant differences, right? But we don't know where those differences are. And so with the post hoc test, once we get a significant difference, then we use our post hoc test to determine between what means are they significantly different, right? And so I'm going to show you two separate techniques that are used. One of the most common ones that's used, which is the Tukey HSD, and then the other one is the Shefe test. Okay, I'm going to show you both, and then we'll get out of here, right? But again, these are run when you find a statistically significant difference, right? So again, F ratio indicates that at least one difference in the means is statistically significant. We don't know which one, right? It does not indicate which means are significantly different. So we use these post hoc tests to follow up to determine exactly which mean differences are significant and which ones are not. Okay. So then I can tell you that group A and group B, they weren't significantly different, but group A and group C were. Okay. So we'd be able to see those two things. Okay. All right. Post hoc test. Again, they are comparing two individual means at the same time, right? So again, that gives us an opportunity for error, right? But each comparison, again, includes that risk of type 1 error. And when we do more and more and more tests, just like we talked about with doing individual t-tests, we increase the likelihood that we're going to get a type 1 error. And the type 1 error, again, that false positive, we reject the null hypothesis when the null hypothesis is actually true, meaning, we say that there are differences when there are absolutely no differences whatsoever. Okay. So we want to be able to take hold of that, right? So the post hoc test, right, they use special methods to try to control those experiment-wise type 1 error rates, right? So again, we try to mitigate, again, getting a type 1 error. We don't want false positives because those things, they don't do really well for our research. Okay, so the first um, test that we're going to be doing is the Tukey HSD test. Okay, and so with this, we are going to use everything that we already have, right? So again, it's a single value, and this value helps us determine the minimum difference between the treatment means that is necessary, right? That we claim as a statistical significance, right? So the main differences that we got, right? So we're going to go ahead and I'm going to go ahead and put this up here so we can see it. So HSD. You remove any square in. Right. So we're looking at our mean differences from our sample. We had mean of 5, mean minus 5, mean 2, 3. Okay. So when I compare, I'm going to go ahead and move. C, A, E, C. Okay. So if I did go 10 minus, let's do, yeah, let's go B minus, B minus A, C minus A, and then C minus B. So we got, we're going to do B minus C, or B minus A. All right, that's going to give me 9 minus 1, 9 minus 5, 4. Okay. I'm going to do C minus A, which gives me 10 minus 5 is 10 minus 5 is 5. Okay. And then I got C minus B. Okay. So that's 10 minus 9 is 4. Okay. So again, I have those differences. Right? And I want to get my 2 PHSD. What is that honestly significant difference that if that number, whatever that value is going to be greater than, that is going to be, if any of these differences falls greater than that 2 PHSD, then I know that I have a large enough significant difference, right? So HSD formula, I'm going to plug in the values here. Let me stop sharing so you can see the big screen. Okay. And the Q value is um, the alpha level, or that value, that critical value that I use using my degrees of freedom. Degrees of freedom for 2 for my between group, and degrees of freedom for 15 for the within group, right? And that value is for Q is 3.68, right? 3.68, and then we use the alpha level of 0.05, and then we have the degree of freedom 2, 15, okay? And then that gives me Q of 3.68. Again, you can locate that on your F distribution table, okay? So we got 3.68 square root, okay? It's gonna be 5.87. This is taken right from my source table, divided by N, or the N number of groups, 6. One thing to be reminded here is for the Tukey HSD test, each sample, each treatment condition has to have the same number of people, right? So since each of our conditions has 6 individuals in it, again, I can use a Tukey HSD test, right? If not, then I'll have to use the Shefe test. We will do the Shefe test, okay? So let's go ahead and calculate this. That's going to be 3.68 times 0.989. Okay, that's going to give me HSD of 3.64. Okay, so now all I have to do is compare this number to all of my differences on the left-hand side here. So maybe open that up a little bit so you can see, right? So I know that there are significant differences between group C and group A and group B and group A, right? Because 4 is greater than 3.64 and 5 is also greater than 4 or 3.64, okay? So again, you get your honestly significant difference, you get your different scores, and then you're able to compare those to determine which means were significantly different, right? So we see that group A and group C and group B, they weren't significantly different, but you did have 2 significantly different. Okay. All right. Let's go back one more time. Share my screen. Let's get these slides shared. Okay. So that is again HSD. All right. So now this is my Shefe test. Okay. I'm going to show you one example of your Shefe test, and then we'll get out of here. Right. So again, with the Shefe test, let me go ahead and clear this out. with the Chef A test, we need several things, right? We need several different things, but I'm going to show you how we do it, okay? So for our F critical, right, a couple of things we're going to need. I'm going to need my mean squared, again, okay? That is 5.87. And again, my critical region, critical F, 3.86. Okay. So then we're going to calculate what we need. Okay. And then we have to remember that my F ratio mean squared, mean squared. Okay. All right. So for the Chef A test, this is one of the most conservative, one of the safest of all possible post hoc tests. Again, it protects us from the type 1 error, right? We're going to use an F ratio to evaluate the significance between any two treatment conditions, right? So again, if you remember all of our treatment conditions, again, we had those differences, right, in our means, okay? We had treatment 1, we had treatment 2, we had treatment 3, right? So I'm going to go ahead and try, let's try treatment A and treatment B, okay? Remember, when we talked about the means, those mean values, let me go ahead and get that, okay? So for the first one, for treatment A, had mean 5. Let's do it this way. Treatment A. 1 second to get that out of the way. Okay, so treatment 5, treatment A, that means 5. Treatment B, that means 9. Treatment C, that means 10. So for the sake of time, I'm just going to do I'm going to do the one for A and B, right? I already know where the significant differences are, right? But I'm going to use the Chef test to indicate that. Right? So I know that the main difference between B and C, no good, right? So I'm going to do the second one. The second main difference is 4, right? So I'm going to do that here. So B, right? Show you how that works, right? So we're doing each individually, right? So we have to find our between variance. We already have our within variance here. We have to find our between order for it. Going to do it again. But let me go ahead and okay. So for the A versus B in squared, that's going to give me, we're going to have this B squared over N minus A squared over B. Okay. So given all that, let's put numbers in. T is, my T for this one was 30. Okay, so let's go ahead and do this. 30 squared over 6 plus 54 squared over 6. That's going to give me this minus G, which is 84. Okay. So again, I'm only using 2 samples. So add 30 plus 54 gives me 84. 6 plus 6 gives me 12 here. And then I just do the work. Okay, so now I have 150 plus 46 minus 588. Okay, so that gives me my assembly squared between 48. Okay. Okay. So again, 48. So now given that, now I need to get my mean square, right? So I get my mean square. And mean square is going to be 20. This is some square. 20 square. 20. Using the same degrees of freedom that I used to. So instead of it being degrees of freedom, 2 minus 1 is going to be 3 minus 1, which is 2. That's going to give me mean square b equals 24. Okay. All right. So again, that is my mean square between, I need that. This is a ratio over equal. So I'm going to stop there, right? I have 4.09 critical value here. Okay. So I know that that difference exceeds the 3.86, right? So there is a significant difference between group A, or treatment A, and treatment B, which is 4 point difference. And since treatment C and treatment A has a 5 point difference, I also know that treatment A and treatment C also have a significant difference there as well, right? Since I already know that B and A is significant, then I also know that C and A is also significant. And in our example, um, B and C, they're not significant at all. It's a 1 point difference. There is no significant difference between those means, just like we saw with the 2 HSD. Okay, so let's go ahead and finish this up, and then I'll finish up. Okay, so again, that's my post hoc test. You got your Tukey HSD, and you have your Shep-Base test. Okay, so again, it says, and this is something that you need to understand as far as how these uh, how these computations are related to one another, right? So it says which combination of factors is most likely to produce a large F value for your F ratio. Okay? So if you look at, again, the F ratio, you're looking at the variances, right? But one of the things that we just talked about when we're looking at the effect size and we're also looking at the Tukey HSD, the differences make a big difference. No pun intended. The differences make a huge difference in how large the F ratio will be. The larger those differences, um, the larger your F ratio will be. Okay, and then also when you have a smaller sample variance, that's really really important, right? So having a small sample variance, meaning that the scores are a lot closer together. That means you're probably going to get a higher F ratio. Okay, so if we're talking about that, that's going to be B, right? So larger mean differences and a small sample variances are probably going to give you the larger value for your F ratio. Okay. Here's another example, another check. Okay, it says true or false. It says post-test are needed if the decision from an analysis of variance is fail to reject the null hypothesis. Right? The second one says a report shows an ANOVA results of F degrees of freedom 2, degrees of freedom 27, F ratio of 5.36, where the p-value is less than 5%. It says you can conclude that the study used a total of 30 participants. Okay, I'll let you pause it. We're gonna go ahead and move forward. Okay, so the first one, the post hoc test, you only need to do the post hoc test if you reject the null hypothesis. If you reject the null hypothesis, you're saying that there are some differences there. I just don't know where they are. And then, since you want to know where they are, you want to locate them, you would use the post hoc test to identify and locate um, those particular differences, right? So you're only indicating that there's at least one mean difference when you reject the null hypothesis. The post hoc test allows you to know where those mean differences are, right? For the second one, that was true, right? So it said that if you go back, you can conclude that the study used a total of 30 participants, right? You got a degree of freedom of 27, right? All you would do is 30, right? You'll do 30 minus 3, right? You have three. Looks like there's three conditions because you have a degree of freedom for between is 2. All you do is, hey, just do it that way, right? And you get your 30 participants, okay? So n minus 1 is 29. 29 minus 2 is 27. Plain and simple, okay? Um, yeah, just more about it. The numerator, again, always measures how much difference exists between the treatments, right? And then the denominator is always going to be measuring how much difference exists within the treatments. And so that ratio, the within treatments group, right? That's when, again, no treatment effect is being shown there, right? Because everybody in the within group is getting the same treatment, right? But between treatments, that's where the effect is really, really important. And so that ratio plays a big part. If the denominator is, again, significantly less than the numerator, you should have a fairly large uh, F ratio. Okay, this has to do with variability, as you can see here, right? When you have a sample, these two samples is hypothetical. They have the same mean difference, right? They have a mean difference of 4 for each of these samples, right? The first experiment A, the variance is extremely small, right? So you see for the between groups, the MS between was 56, and the MS within was 0.667, right? You have an F ratio of 83.96. That's a huge F ratio. That means those differences are extremely different, right? However, look at the experiment B. When you have a larger variance, right? You got 242 for each of them, right? Same mean difference. The between group variance, again, is 56. But if you look at the within treatment differences, the mean square for the within is 40.33 for an F ratio of 1.39. That means that, again, there are no differences whatsoever, right? There are no differences, right? So when you see the variance that is extremely high, there's the likelihood that you're going to get a significant F value is very, very low. But when you have, again, very, very low variances, that's when you begin to see those high F ratios. And that's the difference between variability and F ratios. Okay? When we talk about the F ratio and the relationship between the ANOVA and the t-test, again, you can use either. If you had 2 independent samples, you can use an F test or a t-test, right? The only reason we're going to be using a t-test or F test is because we have more than 2 groups, right? But again, both of these two will give you the same result, right? If you use it, especially if you had 2 independent samples, okay? Again, it's always going to result in the same statistical decision. Again, the T statistic compares distances, whereas the F ratio compares variances, and that's why you can, again, square the T value and you'll get the F value, right? Again, and we're looking at those variances because variances are always going to be positive. T-tests are going to be, sometimes you get a negative value, sometimes you get a positive value, but for any value of a critical region, all you got to do is, again, square the T and you'll get the F critical, right? And that's how they're kind of related. Pretty much the same test, just using and comparing varying ways that they compare the mean differences, right? We're looking at distance between the 2 means for a T statistic, and for an F ratio, we're looking at the variances. But again, both of those things are measuring differences, right? Both of those things are measuring differences just in a different way, okay? So again, if you're looking at a T statistic for the t-test, again, with a degree of freedom of 8, right? You get plus or minus 2.10 for a degree of freedom of 18 for the between, for the within, and for the between, so you have two groups, right? You see that is the total sample was 20, right? But the degrees of freedom were 18. Okay, so you get the same. 2.101 squared gives me my F ratio 4.41. Okay, so again, measuring the same exact things, but just measuring it a little different, right? Distances for the t-test, variances for the F ratio. Okay? Again, just these are my formulas. Know the formulas. I'll provide you with all the information you need. All you need to do is plug in for the formulas to solve for your F ratio. Uh, Use the source table to, again, be more organized in how you calculate those things. And then it should flow for you. It should flow really well. But again, know the formulas, be able to compute using the values that you're given, and you should be perfectly fine on the exam. Okay. All right, we'll stop there. But again, this is the part two. A lot more computation shows you how to calculate a F ratio. We're going to provide you with some practice problems if you want to practice. But again, knowing how to calculate an F ratio is going to be really important for the exam. Okay, I'm going to stop there, but you all have a great evening. Again, F ratio, one-way analysis of variance, chapter 12. I hope you all enjoy.